Every tool this chapter installs is the same move: strip away the substrate and keep the behavior. This section introduces the one gesture the whole book runs on and shows three faces of it. The abstract data type names the structure by the operations it answers to, never by how those operations are stored. An object is what it does. Pseudocode is an algorithm with no particular language clinging to it. Big O is a cost with no particular machine clinging to it. Those are three faces of one forgetful gesture. Discard the implementation, retain the interface. That gesture is the whole book's gesture. Discard the implementation, retain the interface. That gesture is the whole book's governing stance. The chapter exists to make everything that follows language independent and machine independent before a single list is built. Everything after is this one separation applied again and again. The wonder is that what a thing does and how it does it genuinely detach. This section explains the one idea the whole book is built on. The book rests on a single separation made right here. An algorithm's logic is severed from any language that runs it. Pseudocode is the instrument of that cut. It is part English, part structured control, declaring what happens while suppressing the C-specific how. Its natural partner is the abstract data type, a structure named by the operations it admits, never by its byte layout. So a list is what you can do to it. Efficiency analysis and generic code complete the toolkit. They measure cost without timing a machine, and they let you write once across types. Predict every later chapter from this. Trees, heaps, and graphs will each arrive as an interface of operations. First, a serialization. Second, the contract always preceding the construction. This section explains recursion as a structural primitive. Repetition need not be a loop. It can live in the definition itself. An algorithm that names itself inside its own body, where factorial of n equals n times factorial of n minus 1, produces iteration as a consequence of being read, with no counter required. The chapter's entire content is the discipline that keeps this from running forever. There are two parts to that discipline: a base case that returns without recursing, and a general case that shrinks the problem one step toward it. Every call either solves a piece or makes the remainder smaller. The factorial trace exposes the signature. A two-way journey. Decompose top-down until the base. Then, resolve bottom-up. From this, you predict the rest. Anything whose structure contains a smaller copy of itself, trees, binary search, wants this shape. This part explains what makes a process recursive, and why a loop and a self-call are the same thing. A repetitive process is recursive when the algorithm appears inside its own definition. Iteration names only its parameters. Recursion names itself. The chapter's whole arc collapses to one move: replace the loop with a self-call plus a stopping condition. Factorial is the seed anchor. Factorial of n is n times factorial of n minus 1, reaching down to factorial of 0, which equals 1. Every later case, Fibonacci and the Towers of Hanoi, is the same skeleton: a base case that solves the smallest piece, and a general case that reduces the problem toward it. Ye is the generative primitive. Any process whose answer contains a smaller copy of itself can be written by trusting the smaller copy and bottoming out. Recursion is repetition. The loop was never essential. This part explains why a stack is best understood as a single prohibition rather than a built structure. Restrict a list so that data may enter and leave at one end only, and reversal falls out for free. The last thing in is the first thing out. That single prohibition is the stack. Push, pop, and stack top are just the three motions the constraint permits. The generative move is the surprise. You do not build the last in first out behavior. You forbid everything else, and it remains. This is the first of the chapter's 3 restrictive structures, and the footnote names Q and DQ as the siblings. So what it really teaches is that an abstract type is defined by what it refuses, not by what it adds. Constraint is the source of structure, the same pattern every restrictive abstract data type instantiates. This section explains the stack, the structure that comes from a single restriction. Take a linear list and forbid every access point but one end. That single prohibition is the stack. Last in, first out falls out on its own, a consequence of the one rule rather than a behavior anyone adds. With only the top reachable, the newest item sits atop everything older, so it has to leave first. Feed in 5, 10, 15, 20, and you get back 20, 15, 10, 5. The reversal is something the restriction forces, never something the designer arranges. There are 3 operations, all acting at the top. Push writes a new item, pop reads the top item and removes it. Top reads the top item without removing it. The move of this chapter is that restriction generates structure. It is the same primitive that the Q in chapter 4 reuses by restricting the opposite end instead. Think of coins, stacked dishes, the call stack, anything where reaching past the top means clearing the top first. This section explains the Q, the data structure that turns ordering into a rule. A queue is order made into a data structure. You insert at the rear, you remove from the front, and the sequence that comes out equals the sequence that went in. That discipline is called first in, first out. Where the stack from chapter 3 reverses time by reusing a single end, the queue preserves time by separating the ends. That one structural choice, 2 access points instead of 1, is the whole concept. It forces the implementation to track both the front and the rear, where the stack tracked only the top. Every waiting line you know is an instance, the bus queue, the calls on hold, the jobs waiting to print. The chapter's job in the arc of the book is to hand you the first in, first out sibling of the last in, first out stack. It is the same restricted linear list, run under the opposite discipline. This section explains the queue, the simplest data structure whose order discipline is its whole identity. A queue is the discipline that makes service order equal, arrival order. You insert only at the rear, you delete only at the front, so nothing overtakes what came before it. First in, first out. The entire chapter falls out of one move, splitting the stack's single mutating end into 2. The stack tracks one cursor, called top. The queue tracks 2, called front and rear, and that doubling is itself the difference between LIFO and FIFO. 4 operations follow mechanically, and Q adds at the rear. DQ removes at the front. Front and rear retrieval read the ends without removing anything. Overflow and underflow are the only boundary failures. The bus line is the whole abstraction. Everything later is implementation of it. This section explains what makes a linear list general. A list is defined by where its operations may touch it. What identifies it is the locus of access. The storage mechanism is beside the point. Restrict that locus to the ends and you get the stack and queue of the prior chapters. Lift the restriction so that you may insert, delete, retrieve, or change anywhere at the beginning, the middle, or the end, and you have the genywhere or the change anywhere. That single freedom is the chapter's whole thesis. The structural payoff is this. Of its 4 operations, 3 reduced to the same shape, a search to locate, then a local splice. Only traversal breaks the pattern, being a pure loop over every element rather than a hunt for one. You can predict the rest of the chapter from this. Everything is a search plus a one-element edit. This section explains what makes something a list at the level of structural primitive. A list is whatever admits 4 operations: insert, delete, retrieve, and traverse, performed anywhere, not only at an end. That word anywhere is the whole content. It severs the abstraction from its storage, where the stack and queue chapters before it fix the access point, the top, the ends, the general list lifts the restriction, and so must specify the type by behavior alone. An object is what it does. The song list anchor carries it. You search for a song, add one, drop one, and walk them all, indifferent to position. 4 verbs close the algebra. Everything later, array versus linked realization, is merely how those verbs get paid for. The chapter's job in the arc is to name the interface before naming any machine. This section explains what a tree is, built from a single structural constraint. Start with the linear list, where each element has one successor and one predecessor. Strip that assumption, keep only the predecessor half, and you have a tree. Every node carries exactly one incoming branch, save the root, which carries none. That single constraint, in degree 1, everywhere, and in degree 0, at the root, forbids cycles, enforces the hierarchy. The compression the chapter hands you is the recursive definition, numbered 6.1. A tree is either empty or a root sitting above 0 or more subtrees, each itself a tree. Self-similarity all the way down, what a tree is, contains smaller copies of what a tree is. Everything downstream is this primitive +1 added rule. Search trees, AVL trees, heaps, multi-way trees. Learn the constraint and you generate the whole family. This section explains the tree, the 6th body structure in the book. A tree is the first structure in this book that points at itself. It is a root from which descend 0 or more subtrees, each itself a tree. That single self-reference is the chapter. It turns the linear lists of the preceding chapters into branching hierarchy, and it makes every tree algorithm a recursion by construction rather than by choice. One constraint cuts the type loose from a general graph. Every node has exactly one predecessor except the root, which has none. In degree 1 except root is the whole boundary. Relax it and you fall back to a graph. Cap out degree at 2 and you sharpen down to the binary trees. The rest of the book runs on. This section explains the single idea that organizes a binary search tree, the invariant that does all the work. At every node, everything to the left is smaller. Everything to the right is greater or equal, and each subtree obeys the same rule recursively. That local ordering, imposed everywhere, makes a global search collapse into a chain of one comparison per node descents. You never look at a sibling. The chapter's reason for being is a dilemma. It dissolves. Arrays search fast, by binary search, but insert slowly. Linked lists insert fast, but search slowly. The binary search tree is binary search made mutable, the comparison halving of the array now carried out over pointers you can splice in constant time. The catch the title foreshadows is that nothing forces bounds. So an insertion in sorted order degenerates the tree into a linked list, and search falls back to linear time, order n. This part explains how the binary search tree resolves a conflict between two simpler structures. Binary search runs fast but demands a sorted array, where every insertion shifts the tail. A linked list inserts in place but forfeits the power to halve. The binary search tree dissolves the conflict by freezing the halving into the shape. Each node's left subtree holds everything smaller, and its right subtree holds everything larger or equal, recursively. Descending one level is exactly one comparison of binary search, made structural. Order lives in the invariant rather than in any stored sequence, and an in-order traversal reads it back as a sorted list for free. Search, insert, and delete all collapse to a single downward walk. It stays logarithmic so long as the tree stays balanced, the guarantee that Chapter 8's AVL trees will enforce. This part explains how AVL trees keep a binary search tree balanced. A binary search tree degenerates. Feed it sorted keys and it grows into a linked list, the order log n search collapsing to order n. AVL escapes this by maintaining one local invariant. At every node, the two subtree heights differ by, at most, 1. The structural move worth carrying is this: a locally checkable, locally repairable balance condition purchases a global guarantee on height. Each insert or delete can violate balance at nodes along its path. A constant cost rotation, a pointer reshuffle that preserves the search ordering while lowering the taller side, restores it. Height stays of order, log n, always, so search, insert, and delete are all worst-case logarithmic. The price of a maintained invariant, paid in rotations, bounds the worst case. This section explains the AVL tree, the primitive that opens the balance tree arc. An ordered binary tree gives you order. Log n, search only while it stays bushy. Feed it sorted keys and it degenerates into a linked list in a tree's clothing. Order n, the ordering bought you nothing. The AVL tree closes the gap by enforcing a local invariant everywhere. At every node, the two subtree heights differ by at most 1. It repairs any violation. The instant an instant or delete creates one, with a constant cost rotation. Global logarithmic depth falls out of a check. You only ever run locally. That is the chapter's primitive, and the balanced tree arc it opens, a cheap, continuous, homeostatic repair, traded against the catastrophic degradation that an unmaintained structure silently drifts toward. This section explains the heap as a single relaxation of the binary search tree. Start by relaxing the binary search tree's total order down to one rule. Every parent dominates its descendants, and siblings stay unordered. The structure stops being searchable, but it gains one guarantee worth a whole chapter. The root is always the maximum. That is the heap's entire essence, and the source of its two uses, the two the chapter is for. The second move is the structural payoff. Because the tree stays complete, it embeds into a flat array with no pointers. A node's children and parent are pure index arithmetic. You buy extremum at root and pointerless storage by selling the left and right distinction that made a binary search tree searchable. Everything downstream, reheap up and reheap down, is just repairing that one dominance rule after a local break. This section explains the heap as a single ordering invariant, and the two operations that generate everything else. A heap keeps only the order you actually query. Each parent is greater than or equal to every descendant, and nothing more. That single invariant is weaker than a search tree's total left-to-right ordering. it guarantees the root is the maximum while leaving siblings unconstrained, so any repair stays local. The chapter's compression is that two operations generate everything else. Reheap up floats a misplaced leaf upward. Reheap down sinks a misplaced root down. Insert, delete, and build all compose from just these two. And because the tree is complete, it lives in a flat array. The left child sits at index 2i plus 1. The parent at index I minus 1 divided by 2. No pointers are needed. A heap gives order on demand rather than order everywhere. You cannot meaningfully search, traverse, or print a heap. You can only ask it for its extremum. This section explains how raising a node's branching factor flattens a tree. Raise a node's branching factor and the tree flattens. That is the whole move. A binary search tree forces one key and two children per node. An M-way tree of order. M lets a single node carry up to M-1 ordered keys, interleaved with M subtrees the same, less than, and greater than. Invariant now running between subtrees, the same, less than, and greater. Height collapses toward log base M of n, down from log base 2 of n. The author's compression in Chapter 10 states that the binary search tree is an M-way tree of order 2. That reveals the BST as one frozen setting on a dial, a single point on a continuum, rather than a separate species. B trees, the next section, add only the balance, the bare species. This section explains the generative idea behind multi-way trees. The whole chapter rests on a single move. Raise the radix. A binary search tree fixes its out degree at 2, so its height grows as the logarithm base 2 of n. For 100,000 keys, that is 17 hops. A multi-way tree of order M packs up to M-1 ordered keys per node, with M subtrees between and around them, collapsing the height to the logarithm base, M of n. The same key ordering invariant that a binary search tree obeys, M of n. The same key ordering invariant that a binary search tree obeys survives intact. That single move, making the branching factor a parameter rather than a fixed constant, is the chapter's whole generative idea. Every variant that Gilberg and Forouzan build on top of it, the balanced B tree and its kin, is a discipline for keeping that height bound tight. The payoff the chapter is reaching toward arrives when one node equals one disk page. Then fat and shallow beats tall and thin. This section explains what a graph is as a structure and why it sits where it does in the arc. A graph is a binary relation turned into a data structure, a set of vertices plus a set of edges, where an edge simply asserts that this one connects to that one. Every earlier structure was a special case that constrained that relation. A list forces a single successor. A tree forces a single successor. Drop both constraints and you have the general object. Any vertex may connect to any number of others in either direction with cycles permitted. So the chapter's role in the arc is the generalization step. Once connection is arbitrary, the questions stop being, where do I insert, and become what is reachable, by what path, at what cost. Direction, weight, and connectivity are just predicates layered on that one underlying relation. This section explains what a graph is, by the single constraint you remove to reach it. Drop the last constraint on who may point to whom, and a graph is what remains. A list fixes one successor per node. A tree relaxes that to many successors, but holds one predecessor, so adjacency stays a function. A graph keeps neither. Each vertex may have multiple predecessors and multiple successors and multiple successors, so adjacency collapses to an arbitrary binary relation on a vertex set, two sets, the vertices and the lines joining them. This is chapter 11, and its own words are that each node may have multiple predecessors as well as multiple successors. That single release is the chapter's whole identity, and it fixes its place in the book's arc as the terminal structure, the one from which lists and trees fall out as the special cases where the relation is constrained back into a function. This part explains how the sorting chapter is organized and why its structure is the real lesson. Sorting is one operation, but the chapter is built as a genealogy. There are 3 primitive moves. Select the extreme element, insert into an already sorted prefix, and exchange out-of-order neighbors. Each in its naive form costs order n squared, and each one sees a fast order n log n descendant that breaks the quadratic wall by exploiting structure the primitive ignores. Shell sort grows from insertion, heap sort from selection, quick sort from exchange. The taxonomy is the thesis. The slow sorts are the conceptual seeds of the fast ones, not merely bad alternatives, so learning the cheap 3 is learning the expensive 3. A second axis, internal versus external, marks only whether all the data fits in primary memory. This section explains how 6 sorting algorithms collapse into 3 underlying moves. The chapter's real claim is that the 6 algorithms reduce to 3 moves, 3 ways, an element reaches its sorted position. Insertion slides each new element back into an ordered prefix. Selection scans the unsorted tail for the extremum and places it. Exchange repeatedly swaps out-of-order neighbors. Here is the generative payload. Each family has a naive member and a fast member, and the fast member is the same move made cheaper. Insertion becomes shell sort, which is gapped insertion. Selection becomes heap sort, which is selection through a heap. Exchange becomes quick sort, where partition is a bulk exchange. Learn the 3 primitive moves and the advanced trio predictions. Orthogonal to all of this are 2 further properties: order, meaning ascending or descending, and stability, meaning whether equal keys keep their input order. These are attributes a sort has, not a family it belongs to. This section explains how searching works as a single trade. Finding a target's location is governed by one trade: how much structure you exploit before you start comparing. With none and unordered array, you scan element by element, every comparison earned the hard way. Order the list in binary search spends each comparison to have what remains. The chapter's real leap is hashing. Stop comparing and compute the address from the key itself, so searching collapses into addressing. Constant time in the ideal case. Every algorithm here lives on that one axis, comparisons traded against pre-computed structure. The price of perfect addressing is collision. 2 keys claiming 1 slot, which is why the chapter ends on resolving it. This section explains how searching trades structure for speed across 3 algorithms. Searching is comparison repeated until you can stop comparing, and the chapter's arc is the steady purchase of less comparison with more structure. Sequential search assumes nothing and pays for it. You walk the list, order n, impose order, and binary search halves the unknown each step. Order log n, the ordering is the structure bought. Hashing abolishes the walk, the key itself computes its address. Order 1, with collision resolution as the rent on that move. One generative move runs across all 3 algorithms. Every speedup spends imposed structure to buy away probing. From this, you predict the next instance. Faster lookup always means the position was decided before you looked.